So this problem is basically also on relative motion. So point A moves uniformly with velocity v, so that the velocity so the vector v is continually aimed at point B, which in its turn moves rectilinearly and uniformly with velocity u less than v. So both the magnitudes of the velocities of the particles are the same, but for point A the direction keeps changing. So basically the only the magnitude is constant, whereas for point B um, moves rectilinearly and uniformly. So direction is also same, magnitude is also same. So at the initial moment of time v is perpendicular to you and the points are separated by a distance L. How soon will the points converge? Okay, fine. So let's now consider points A and B. Let's say they are points A and B are initially L distance apart, and point A always is aimed towards point B with a velocity of magnitude v, and v is perpendicular to u. So let's say it's this way without loss of generality. So that's the case. So now let's consider, and and at all times A is directed towards the motion of B. So let's say after a certain instant B is here, A is, let's say, here after a dt time, very small amount of time, and the velocity will be in this direction. It will move a little towards here, this will move towards here after some time, so it will be in this direction until eventually it catches up with B. So essentially, I draw it once more. B will be going in this direction. A will start perpendicular to the horizontal direction, but eventually meet B at some point. Okay, so and its velocity direction will always be directed towards the location of B, right? So let's say at some point, at any point t, okay, so the direction of velocity is, let's say, this is the v magnitude direction, the horizontal is, let's say, alpha, let's say, and it is directed towards B at that point t, and B's velocity magnitude is u. Yeah, so and also just B which moves rectilinearly and uniformly with velocity u less than v, right? Okay, so now we need to consider two things. First of all, A and B initially were separated by distance L, alright, and if we consider it sitting on B, that is in the reference frame of B, the A and B keep, so B keeps approaching, sorry, A keeps approaching towards B, and the length L reduces to 0 upon convergence. So let's say this is at t equals this point is after some t equal to tau. Let's say this means what? This means that after t equal to tau, if we calculate the distance that is moved, like in the reference frame of B, whatever is the basically the distance moved by A in the direction of AB. Let me write this: distance moved by A with respect to B in the direction of AB, that is basically the line joining the two particles. A and B are the particles, not the points, they are the particles, is basically okay, till convergence, that is till t equal to tau. So what is this distance? L, right? So how do we calculate the distance we do it, since one thing is really important here, the direction joining the 2 points, right? So this is the basically the line joining the 2 points from here to here at some point t. So it has a component of u cos alpha in that direction. So basically that L is, so okay, we can write it this way. So with respect to B, okay, with respect to B, the velocity of A, VAB, so with respect to B, in the direction of AB, right? In that direction, what is the component is what we'll see. That is nothing but V, which is the velocity magnitude of A, minus u cos alpha, which is the velocity magnitude of B. Okay, this is V of A with respect to B, and we already know that what is the distance. So what does this mean? And alpha also, this alpha keeps changes with time. So obviously, since it changes with time, you can say that L is equal to an integral of from 0 to tau this velocity V minus u cos alpha times dt, because this alpha is changing with time. That is why integration. This is one equation, right? But obviously we don't know, I mean we need to find out what is tau, but we don't know what is alpha, where is with time, and also we need a second equation. Now here what we'll see is like here the other equation is basically that the initial so if we consider this axis, let's say we call it the x-axis, in this direction basically the relative displacement between A and B is 0, because initially also they were basically, since this was perpendicular, they were, yeah, horizontally they were separated at 0 distance. When they meet also they are separated at 0 distance. So we consider the horizontal components. We have here V cos alpha and U, and relative to each other. So in the horizontal movement, relative movement, of course, the displacement is 0, and that is integral again 0 to tau, and in the horizontal direction it is V cos alpha, right? V cos alpha minus U dt. Okay, right. So now we have to find out tau. Now of course we don't know what would be the value of integral cos alpha dt. We don't know how alpha, I mean where is it time, but we can eliminate using these two equations. So let's expand the first equation. So L equal to, so this is a constant, V is a constant, there is nothing but V tau, right, into tau minus 0 minus U times integral from 0 to tau cos alpha dt, and so this is 0 anyway, so this becomes U tau. So I'll just write it as U tau because it's a constant. V into integral of 0 to tau V cos alpha, sorry, 0 to tau cos alpha dt, right? So what we can do is we can multiply V over there and U over here. So if we multiply this by V, multiply this by u and add. Of course, these two terms will cancel out, minus uv plus uv. And so, yeah, what will happen is v into L is equal to v square tau, right? Okay, I rewrite it again, sorry. So it will become v into L plus u square tau is equal to these integral terms will cancel out, because vu, yeah, into integral of cos alpha dt from 0 to tau. What will be left is v square tau, right? This means we bring this to this direction. Tau will be equal to vl divided by v square minus u square, right? So the time taken is basically vl divided by v square minus u square for the convergence. So yeah, that is that. Thank you.